Okay, welcome everybody to the Northwest Quantum Nexus seminar series. We are very happy to have you here. Today we have Aram Harrow presenting, and Guang Hao will introduce him in just a bit. But before that, we wanted to make some announcements. First, this seminar is being recorded, so by attending this meeting, you may appear as an attendee in the recording, and your questions and comments in the Q&A will also be part of the recording. The Northwest Quantum Nexus has a code of conduct. The NQN is dedicated to providing a respectful, friendly, professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that is harassing or degrading to any individual in any form. Individuals are responsible for knowing and abiding by these standards. We encourage everyone to assist in creating a welcoming and safe environment. NQN reserves the right to refuse admittance or remove any person from an event at any time at its discretion. If you're interested in hearing more about upcoming events with NQN or just learning about NQN in general, our URL is in the bottom left of the screen here. Also, we are having a little bit of a mix-up this time with Teams. Some people are being admitted as presenters. Please keep yourself on mute unless instructed otherwise. If you have questions, you can post them in the Q&A window and we'll moderate them then. And please bear with us as we figure out what's going on. So Guang Hao, without further ado, can you introduce Professor Harrow?
Thanks, Nathan. Aram is an associate professor of physics at MIT, where he has worked since 2013. Previously, he worked at the University of Bristol and the University of Washington. And before that, he did his undergrad and PhD at MIT under Professor Isaac Chuang. His most highly cited paper is Quantum Algorithms for Linear Systems of Equations. This is a very famous paper in 2009 with 1,415 citations. This was a breakthrough result in much of that facilitated much of early quantum machine learning. And he is also the recipient of the 2009 APS Outstanding Referee Report, the 2015 NSF Career Award, the 2017 IEEE Information Theory Society Best Paper Award, and the 2018 APS Rolf Landauer and Charles H. Bennett Award in Quantum Computing. He has also served as the PC chair for TQC and QIP, as well as also has served as a member of the steering committee for both conferences. He's also a founding editor for the Quantum Journal, and more recently his work has focused on precisely the topic today, which is hybrid classical quantum algorithms. So now I give the floor to Aram so that we can learn more about his exciting research.
Thanks, Guang Hao, for the nice introduction, and thanks to everyone for inviting me and for coming. I have to share my screen. I want to share, yes. 1 second. Good, do you guys all see some slides? Actually, I'm told that, actually, I see only Guang Hao. So Guang Hao, give me a thumbs up if you see my slides.
They're up.
Good, good. Let me add one thing to the, which is please interrupt me with questions if you have them during the talk. I know sometimes they don't appear immediately, but you know, I prefer to get to them in near real time instead of at the end, because I'll talk about a few different things, and it's always nice to answer questions while the things are still fresh in memory. I'm going to talk about a few different papers. So these are two that are out, and then there are a few from my group that are hopefully going to come out pretty soon, on the topic of how classical and quantum computers can work together to solve problems that they otherwise couldn't. And one of the starting points for my thoughts here was the fact that when we talk about algorithms in, say, quantum machine learning, or the one that Guang Hao mentioned, my work on linear systems of equations, the importance of the utility of the algorithm often depends in a very important way on the input model that's used. And I've been finding that thinking about different input models for quantum algorithms is a useful way of organizing my thoughts on what we can do with different quantum capabilities. So the standard, by the way, do people see my mouse cursor? Does it look like a little pointer? Make it a little laser pointer.
We don't see the pointer.
What about now?
We see it.
Okay, good. So the standard model of quantum algorithms is sort of what you might expect for a Turing machine. The input is a bunch of bits, and the output is one or more bits. These correspond to the sort of easiest to state problems like factoring an integer or 3-set, combinatorial optimization problems. And that's often what we ultimately want to do, because at the end of the day, our quantum computer is going to get the input from a classical computer and then return it to us in some sort of form that's legible to us, meaning as a classical bit string. Leaving aside important applications like quantum sensing that I just don't want to get into right now. However, it's productive to think about quantum algorithms in a broader range of models. So one of them is the input is still an n-bit string, but it's given to us via an oracle or implicitly. So as you can think of the n-bit input as being the truth table of a function that takes on n different inputs. And there's an oracle O that will give us random access to this bit string. And many, many important algorithms fall into this category, like Grover search, as well as more sophisticated variants like the NAND tree, the collision problem, as well as many provable exponential speedups like the hidden subgroup problem and the welded tree problem. So the oracle model gives us a diverse range of important speedups, but you have to think, after you have an oracle speedup, how do you convert it to a speedup in the standard model? For example, you could use Grover to speed up your 3-set algorithm, and then evaluating your 3-set instance would basically be you instantiating the oracle for Grover search. But Grover search by itself doesn't directly give you a quantum algorithm in the standard gate model. These two are nice because they are comparable to classical. It sort of lets us have a fair fight, a fair comparison with classical algorithms. But it's also productive to think about other models that only make sense in the quantum model. So the input could be given as a string, as of n complex numbers, which specify the amplitudes of a quantum state on log n qubits. This is called the quantum data model, and it's used for the linear systems algorithm as well as the quantum Fourier transform, quantum simulation, and many other algorithms. So you could say, what's the key difference between the regular classical Fourier transform and the quantum Fourier transform is that they're achieving incomparable things. The classical Fourier transform is working on a list of numbers. The quantum Fourier transform is working on a list of amplitudes. Again, not a complete algorithm by itself, or rather, it doesn't achieve a classically useful computing task by itself, but it's an important subroutine in problems that we want to solve. And finally, of course, we can have a quantum oracle where there's a black box unitary, and this sounds a little abstract, but even this is routinely used. For example, this is the model of phase estimation, as well as more recent things like the quantum singular value transform and qubitization. You could think of them as also working in this quantum oracle model. And if you look at Shor's algorithm, actually all of these show up at some point, right? It uses phase estimation, uses the quantum Fourier transform, uses the hidden subgroup problem, period finding. All of these show up at some point on the way to Shor's algorithm. So with this in mind, it's worth revisiting, one of the pillars of quantum algorithms, Grover's algorithm. And Grover's algorithm, misleadingly, was the original title was a quantum mechanical algorithm for database search, but it very much is not that, because it uses an oracle, not a physical database. You could say an implicit database, the truth table of a function, not an actual database on a hard drive. So the right way to explain Grover's algorithm is to say, given the way to compute a function f, where f of I is x of I, and so the truth table of f is the n-bit string x1 through xn, we want to find an input that will such that that the function evaluates to 1. Classically, of course, you need time order n. Quantumly, you can do it with square root of n queries. And since then, people have found many quadratic or otherwise polynomial speedups for a wide range of unstructured or semi-structured search, optimization, and optimization problems, like maximizing a function, approximately counting the number of ones, graph problems, game tree evaluation, and so on. So we have Grover's have been widely generalized to the point where if you see a problem without much structure, it's a reasonable guess to assume that you'll get a square root speedup. Not always true, but more often than not. However, what about that oracle? How are we going to turn that into something practical? Here's a picture of a data center. And if you try to do Grover search over records in that data center for one that matches your some conditions, it's not a very good idea. You send in a superposition of addresses. You say, I'd like to query a superposition of address bit number 37 and bit 40,022,000,022, right? And the data center is classical hardware, so it will effectively measure the input that you send in and collapse that superposition down to a classical value, right? It's not quantum hardware, so we cannot query it in superposition. Even if we could, that would not be the best way to go. If we have a gazillion hard drives, we have, I don't know, a gazillion over 4 CPUs attached to those hard drives. They might not be the most powerful ones, but they're definitely the amount of computing scales with the amount of storage, and so we should just do our algorithm in parallel. And so sequentially stepping through, whether on a quantum or a classical computer, is not the way to go for this kind of search problem. Now, you could posit a quantum RAM, which is a type of hardware that could be queried in superposition. And this is a very interesting question to ask, what can you do with quantum RAM? Sometimes it gives you some powerful capabilities. This is a useful line of work, but not one I want to engage in myself. Basically because as a theorist, my time is cheap. Experimentalists work very hard. And I would just like to ask them for a conventional model of quantum computer. I don't want to ask them for some additional capabilities that go beyond what they're already struggling to achieve in the lab. So, what can we do with sort of the standard model of quantum computing to make Grover's a useful algorithm? And what can we do about oracles in general? So if we have a bit string that lives on a hard drive and we want to turn it into a quantum oracle, something a unitary where you put in index I and you unitarily extract the bit x sub I, how can you do this? Well, one way is you can do it in time order n. So you do a series, there's a sequence of gates that will check the first register, see if it's equal to 1, and if so, add x sub 1 to the second register. If there's, if I is, and then, go on to the next one. If I is 2, you add x sub 2 to the next register, and so on. This can be achieved in the conventional model, so that the quantum computer is in no way looking at the big hard drive. Instead, imagine that you have, let's say the quantum computer is controlled by there's some signal generator sending in pulses. This is controlled by an FPGA that's talking to a laptop, and the laptop reads one record off the hard drive, figures out the corresponding quantum gates, and sends them to the FPGA. It does those gates, and then the laptop reads the next record. So there's no sense in which you need a lot of quantum memory to store all these records. They're never getting stored in the quantum computer, rather than being turned into some sequential operations. So it fits very naturally into our computing model. However, the overhead is devastating, right? Having an order n overhead wipes out all possible oracle speedup. I should say this is not exactly the best possible. So Guanghao and actually some other Microsoft co-authors who are probably on this call.
There was also Luke from MIT. Luke Schaefer.
That's right. Yeah, and Luke. Yeah, Luke Schaefer.
And right. From us was Vadim and myself.
And Vadim, right. Sorry, Vadim, yes. And Vadim, Luke, and Guanghao wrote this cool paper where they can reduce it a little bit, but you can't get it down that much. So what do you do if you really want a big speed up in this model? As I mentioned, one possibility is posit a QRAM, which is good as far as it goes, but it's also worth figuring out what can we do without it. And then the other possibility is come up with a function for which your desired string is the truth table. This is what Shor did. He said, okay, well, we have if you have an oracle with a period, then there's a quantum exponential speedup for period finding. Now, the challenge is to come up with a function that has an exponentially large period that you can efficiently compute the function, and extracting the period is a useful activity. So for factoring, if you take f of I to be a to the I mod n, that fits all of those criteria. However, in the 27 years since Shor's algorithm, it's been hard to come up with functions that meet all of those criteria, right? Use efficiently to evaluate, give you something useful that you cannot do classically, etc. And we wouldn't expect that for kind of a generic machine learning problem, right? Where you just have a bunch of data you found on the internet. You would not expect some kind of simple generative model that has all these properties. So instead, the approach I want to propose for this big data setting is to find problems where we can reduce the size of the data set. And these will be problems that are hard problems, but not contrived. Problems like clustering, Bayesian inference, and saddle point optimization are all kind of widely studied problems in classical statistics. So that's the first thing I want to tell you about in this talk is how can this hybrid approach tackle problems that involve statistics using data without any kind of funny assumptions about hardware. So to be concrete, let's talk about maximum likelihood estimation. In this, you have a set of models Y, and you have a data set X, and the problem is to find the model that best fits your data. And this will assume that the data set is a set of points that are drawn IID from some distribution. Let's say the probability of X given model Y is P of X given Y. Take the log of that and you call it F of XY. Then the log of the probability of seeing the entire data set is just the sum of these individual F of XY. So the thing you want to maximize over all models Y is the sum of all the F of XY. Then sometimes we want to add another term that tells us maybe even before we've seen any data, some models are more likely a priori than others. Sometimes this is called maximum a posteriori estimation once you add this R of Y term here. But it's almost the same problem. So how hard is this to do? Can we get a quantum speedup? If you look at it, the sets X and Y in terms of the math equation appear almost symmetrically. You have a maximum over Y and then a sum over X, but Grover can get a roughly square root speedup for both of these problems, for both maximizing and summing approximately. But the types of data are very different. X is an actual data set that lives on a hard drive, so we do not have superposition query access to it. Whereas Y is one of these synthetic data sets, something that we can make superposition queries to. For example, if we're searching over clusterings, then Y might be the set of all possible ways of choosing 12 cluster centers in our 20-dimensional space. And maybe the clusters have some covariance matrices to them. They don't have to be isotropic. And there's a gazillion possibilities here, but we don't have to actually enumerate them all on a hard drive. We can, we can make random access to these. We can index them and search over them with Grover if we want. So what that means is that in our model of a classical computer controlling a quantum computer, which I think is the most natural model of a quantum computer, the number of quantum evaluations of F that we need will scale like the size of the data set X times the square root of the size of Y. So in our outer loop, we can do a Grover search over Y, and then with runtime square root the size of Y. The inner loop, we're stuck just doing that sum over X. There's no quantum speed up there. And so this hurts from a quantum algorithm's point of view. You can imagine maybe you have an even more clever quantum optimization algorithm that gets a better than square root dependence on the size of Y. But still, if the data set is large, that inner loop, you're paying the same price quantumly as classically, and that's going to potentially erode a lot of the quantum advantage. So the question I want to consider is, can we reduce the dependence on X so that the quantum advantage will become more significant? And the approach I want to propose is one that's well studied in the classical machine learning literature. Started off as a technique in computational geometry and then moved to machine learning and statistics. It's called a coreset. The idea is if you have a data set X, you can approximate it by a smaller data set X prime. Probably, I guess I should have written along with some weights. And we say that X prime is a coreset if for all models Y, the true log likelihood on the left-hand side is well approximated by the log likelihood when you only sum over the points in x prime, and you have to add some weights to them. If nothing else, you can see the number of terms. If x prime is a lot smaller than x, there are going to be many fewer terms on the right-hand side than the left-hand side. But the interesting case is actually when the weights are unequal. So if you think of a clustering problem, one way to construct x prime, or at least the ideal way if you had perfect knowledge of where the clusters were, is you would choose a similar number of points from each cluster. And so that means if you have a really big cluster, you'll choose, let's say, 3 points, and a really small cluster, you'll also choose 3 points. And that is, in a way, unfair to the big clusters. They're weighted less than they should be. And so you compensate for that by boosting their weight, this W of x term, for the points that you do select. And this is you can say this more formally, and then this leads to something called importance sampling, where you choose something with some probability, and then the weight you give it is 1 over the probability of choosing it. So this gives rise to a simple and general class of hybrid algorithms for machine learning. You have a big data set X, you feed it into a classical computer, and it spits out a coreset X prime, which is then fed to your quantum computer, which then outputs the best model it can find, Y. And in a little bit more detail, how do you? So I said if you have perfect knowledge of the clustering, turns out one thing you can do is you can get an approximate clustering. Let's call it Y prime. It can be approximate in the sense that not only is it not the best clustering, let's say that uses the desired number of cluster centers, let's say 5, maybe it uses too many, maybe it also uses too many cluster centers, let's say 20 cluster centers instead of you ultimately want to come up with 5, and maybe it's a very crude approximation even for 20 cluster centers. So this you can do with algorithms like the k-means algorithm. And then using this, it's still good enough to construct importance sampling weights. And it turns out the quality of the approximation at this stage doesn't affect the final quality of the approximation you get. It only constructs the size of the coreset, which then governs the runtime of the next step. So using this crude estimate, you can construct importance sampling weights, which you can use to construct the coreset. Then you use the quantum computer to carry out your optimization on this coreset. And here I've been saying everything in terms of Grover, because for a few reasons. Grover has a clearly defined, we know what the speedup is for Grover. And so it lets me say things in a more concrete way. Also, it's always bothered me that I just want to understand Grover better. I feel like we should at least understand Grover before we move on to more complicated things. However, you might object that square root speedup is not going to be enough to make a quantum computer economically viable. So ultimately, we're hoping for a better speedup, and the point is, whatever that better speedup is, that's going to be a speedup relative to the size of Y. Or maybe I haven't talked about the structure of Y. Maybe you can take advantage of that. In any case, that's going to speed up the search over Y. However much you speed that up, you still want to drive down the cost of the inner loop, which just depends on X, and for which there's no quantum cleverness. And so now the inner loop is driven down to the size of X prime, and the total cost is the size of X prime times however long it takes to search over Y. So square root of the size of Y for Grover, maybe something better if you have a better algorithm adapted to your problem. But whatever it is, that speedup is going to be more significant if it's multiplied by something smaller than the size of X. And for problems like clustering, so I should be careful when I say provable speedups because we don't know the true classical complexity. But if you take the best, rigorous analysis of a classical algorithm, what can we prove about finding the clusters to a certain approximation error on a classical computer? Then this gives us a nearly quadratic speedup for this problem if you Groverize it on a quantum computer, because it boils down to finding a coreset and then brute forcing over clusterings of that coreset. And so now, after doing all this business with the coreset, we're back to a combinatorial search over a very large space specified by a small amount of data, which is which is the area where Grover speedup shines. So yeah, I should maybe pause here for any questions before I move on to different algorithms.
All right, so one question is, couldn't you classically compute these guesses of y prime? How does the quality of the quantum computed y prime in determining sampling weights compare to what you could get classically?
How does the quality of y prime, sorry, repeat that last part?
Right, so in the classical case, if you have already gotten the coreset x prime, then the classical algorithm will have a runtime that scales with x prime. So it seems like the advance here is that you can compute x prime more effectively.
No, sorry, we're x prime. Well, that's not my advance. That's just from the classical coreset literature. So in the classical coreset literature, they already found a way of computing x prime. And indeed, a fair comparison, like what is the best classical algorithm? The best classical algorithm also uses x prime. And then it has to search over all clusterings of x prime. And so, so really all I'm saying here is really there's not very much technical depth to it. It's just to say that this is the right framework for applying Grover. Start with this type of classical algorithm where you are spending a little bit of time to construct a coreset and then a lot of time to search over clusterings of that this is sort of the right way to try to have a quantum computer deal with a big data set. And the quality of y prime, I'm leaving out the quantitative details, but what is the quality of y prime effect? Basically, x prime is an approximation of x. And if you want to get a better approximation, you sample more things in x prime, but then you pay the price because you have to search over a bigger space. And how large does x prime have to be to give you a good approximation of x depends on how good an approximation y prime is. So if you choose a good y prime, then you don't have to make x prime too big, and the quantum computer doesn't have to work for too long. If you have a lousy y prime, you have to sample more points in x prime, and the quantum computer has to work harder. And it still turns out that the runtime depends only on the complexity of the problem, things like the pseudo dimension, which is kind of like the VC dimension, the desired accuracy, and parameters like that. Does not depend on the, in general, does not scale with the size of the data set. So for clustering, it would depend on the number of cluster centers, and the dimension and the desired accuracy does not depend on the original number of points. But yeah, that's where, so the quality of y prime, though, does ultimately affect your runtime by affecting the size that you need of x prime.
I see, thank you.
Any other questions?
So another question would be, you've mentioned that, with this approach, you can get Grover style speed up, so that maybe Grover is not enough because of the finite and slow clock speed of quantum computers. So
yes.
What potential is there for super Grover speedups in this model?
Ah, good. Yeah, well, that's another talk. I'm working on, with Tongying Li and my student Shankar Balasubramanian, we've been working on trying to get super Grover speedups with quantum walks. So the dream is, you search over some kind of solution landscape and your quantum walk reaches the target much, much faster. Tongying has this intriguing example of escaping saddle points where he has a cubic speedup there. And I really like Matt Hastings' short time adiabatic evolution, which also can give you a beyond Grover speedup in some cases. And just to zoom out, to summarize the situation, there are some intriguing examples of beyond quadratic speedups for somewhat realistic optimization problems, not like super contrived, but they're not. Yeah, I would say we do not know the scope of these. We don't know how much we can expect to get away with here. So, yeah, we're hopefully we'll have our quantum walks paper out in a few months. Maybe sometime I'll come back and give a talk about that. And I think there are many promising directions, but nothing you know, if you want the combination of a giant speedup and very general, you know, we still so far definitely lack that. So Grover has a lot of generality. These other speedups are rather specific. They're improving, but there's a long way to go.
All right, thank you. We look forward to this future talk.
Yeah, thanks. And so, okay, so in this algorithm, I think it's a useful way of looking at things, but, and you know, to be honest, it's good to approach problems from the perspective of what is the minimum number of resources to solve the problem, and it doesn't matter if those resources are quantum or classical, right? But as a quantum computer designer, I would really like to have a more glorious role for the quantum computer, right? Because if you look at this, you could just say, well, really, this problem was not as hard as we had thought. Like for clustering, it turns out you don't need 1 trillion data points because the data sets are well compressible. You can compress them down to a coreset. So, you know, it's not that you have a clever algorithm. It's just that the problem was not as hard as you originally had thought. So, what I would like to do instead is find ways where the quantum computer can meaningfully interrogate the entire data set, where it depends even on a single data point can shift things. Is there a way of using the quantum computer interactively to do this, to query all the data points, not just the handful the classical computer hands you? And there is a literature on adaptive coresets. The second paper is a review. This first paper has a specific idea, which I think is promising. And for a problem a little bit different than clustering, a different problem of Bayesian inference. So here, the problem is not to pick the most likely model, but to sample from the posterior over models. You have a prior pi naught, posterior pi. You want to sample from pi. And the idea is this will give you not just very likely models, but it'll give you some sense of the uncertainty interval around the most likely model. And one way you can do this on a quantum computer is in step T of the algorithm, you send data points x1 through xt along with their corresponding weights to the quantum computer. Then the quantum computer samples from the, not the true posterior, but the posterior you get from, basically using this coreset, replacing the full data set with this weighted subset. And then the classical computer goes back, looks at the data, and says, okay, well, given these models, y1 through yt that I've seen so far, what is the most informative point I can add to my set? And so you can do things like saying, well, what is a point that is not well fit by these models? Let me add this to force the quantum computer to take account of that in the next iteration. And this can do things that you couldn't do with non-adaptive, this first model where the classical computer just crunches the data, just sends it to the quantum computer. These interactive protocols can achieve more. Another nice thing here is that, how can a quantum computer speed things up? Well, you can do a Grover like algorithm to quadratically speed up rejection sampling, just like Grover search is a quadratic speedup of brute force search. But brute force search and rejection sampling are usually not the best algorithm. And what's nice about sampling is that you can also get a quadratic speedup. And here I have a small improvement to the previous work here with my student Annie Wei. You can speed up what we show, building on the work of originally it was Pavel Wojcin and actually many other people, Abe Asinga and several other people. Basically, you can get a quadratic speedup of simulated annealing, which is a much better algorithm than rejection sampling or brute force search. So in simulated annealing, you have this sequence of Markov chains, starts off by bouncing around at random, and then you gradually lower the temperature. This is not the best classical algorithm often, but it's a quite competitive one, and this can be quadratically sped up quantumly. So you can quadratically speed up something that is already a quite competitive classical algorithm. And so I think this is a pretty promising thing to do on a quantum computer. Now, how do you choose this next point to be most informative? Campbell and Broderick have a proposal, which I don't want to get into because this is really, sort of orthogonal to what the quantum computer does. They have a way of kind of representing the data points as vectors and basically creating a kernel from y1 through yt. Their approach is sort of heuristic in that the performance of it depends on parameters that we don't know, that that don't just depend on the size of the set. It's sort of like the gap of a Markov chain. Your performance depends on that. You don't know what it is, but still it's a promising heuristic. Instead, I'm going to talk about a third problem. So we talked about clustering, Bayesian inference. I'm going to talk about a third problem where we can use these adaptive methods to get a provable performance guarantee, and one that is often quite close to optimal. So this problem is saddle point optimization. Again, I'm going to have a classical data set x1 through xn, but now I'm going to find capital X to be the convex hull of these points. So that's just sort of a little picture of a convex hull. It's the smallest convex set containing the points. And Y is not going to be a set of models, but it's going to be convex combinations of those models. So if you're familiar with boosting, this is a situation in boosting. You don't just output one model to fit the data. You can output some mixture of models that on average fits the data pretty well. And the cost function f, I'm going to have be linear in x and y. So the score of a model, if I have like a mixture of several models, the score is just the corresponding weighted average of the scores of those individual models. And what I'd like to do is choose the best model that is, choose the model that does the best on the worst data point. So I'm going to maximize over models, the minimum over data points of f of x, y. And because of these convexity and linearity conditions that I've chosen, von Neumann's minimax theorem applies, and I can reverse the order of the min and the max. So I can instead minimize over x and then maximize over y. Those give me the same answer. So this is called saddle point optimization, because you can think of it as, in one direction I'm maximizing, in the other direction I'm minimizing. And this family includes several problems that are several useful problems. So one of them is zero-sum games. So the X player wants to minimize, the Y player wants to maximize, and they each have some strategy set. The important thing here is that the X player strategies should be specified, again, by a physical database, whereas the Y player strategies we should have superposition access to. And you can imagine this happening in many cases, like, let's say that the set X is some list of customers and Y is some way of meeting their demands, and you want to choose, like, placing cell phone towers, something like that, and you want to choose some way of placing them in a way that no customer has bad coverage, right? So then the set Y that you're optimizing over, you have some combinatorial set of choices, whereas the set X is something that is, an actual set of data. It also includes linear programming. So if the set X specifies linear constraints over Y, so each X is a hyperplane, and f of x, y is positive or is non-negative if the constraint is satisfied, and it's negative if the constraint is violated. Then if this value is negative, then the thing is infeasible, and if it's non-negative, then it's feasible. It also looks kind of like maximum likelihood estimation. If we replace this minimum with the sum, then we're back to maximum likelihood estimation. And so if you think of a clustering type problem where you care not about the average performance, like the average over points, but about the worst case point, then that's basically this problem. And this also is equivalent to SVMs if we use the L1 norm instead of the L2 norm. And there's it's not a very deep connection, but just requires a little more notation, but it's described in our paper if you want more details.
So we got a question with regards to the previous slide on the adaptive coresets. So is it accurate to think of this as an example of a quantization of particle filtering, which is a technique used in classical sampling?
I am a little fuzzy on exactly what particle filtering is, so I cannot answer that. I'm sorry. But I will, if whoever the questioner is emails me, I'll look up particle filtering and get back to you. Yeah. Or is there a very quick explanation of particle filtering?
I'm not an expert in it myself. Sorry.
Yeah, I saw at one point a description of particle filtering that looked similar to this, but I don't know enough to give an accurate answer right now. Okay, so let me explain this algorithm, and to explain it, I'm going to use the zero-sum game perspective because I think that's makes it very intuitive what's going on. And here is a hybrid algorithm for solving a zero-sum game. We'll use the example of rock, paper, scissors. So here is the payoff matrix. Remember, the X player wants to minimize, so their payoff is negative, whatever is here. The Y player wants to maximize, so their payoff is positive, whatever is here. And the algorithm is due to Grigoriadis and Kachan. And you can imagine basically these two players playing against each other, but they do not want to play perfectly. If they did best responses, you can see very quickly you would just cycle, right? Like, well, let's start off with pick X1 arbitrarily, let's say rock. So if Y chooses paper and then X chooses scissors, this is just going to go in a cycle, will not converge. But if you add a little bit of noise, it converges rapidly. So what we'll do is we will have some parameter epsilon, and we'll, which actually relates to the desired accuracy that you want in the end. The Y strategy will be chosen with probability proportional to e to the epsilon times the payoff. So let's suppose, so paper will be a little bit more likely, scissors will be a little bit less likely, because paper is the winning strategy. So we do not always choose paper, but choose it more often. And so let's suppose we happen to choose paper, then we go in the other direction, and this induces some payoffs now for X, and we do the same thing, except with a minus sign here, because X wants to minimize. So now rock is the most, scissors are the most likely, rock is the least likely. Let's say that X happens to choose paper, because it's random, anything's possible. Now we go back to the Y player, and we do the same thing, except now we respond to the sum of all of X's actions so far. So we take these two rows together and add them up. And if we repeat something, we just add up with the appropriate multiple. And so what happens is, at first the players are bouncing around at random because they're choosing from nearly the uniform distribution, but the bad strategies start becoming exponentially unlikely to be chosen. And so this thing converges to a near Nash equilibrium. And what they prove is that the convergence scales very well with the number of strategies, although not so well with the desired accuracy. So if you want an error that's epsilon times the largest entry, largest possible payoff, the number of rounds you need goes like log of the number of strategies, which is great, divided by epsilon squared, which effectively means it doesn't permit a very small epsilon. This will only work for some modest values of epsilon. But in that case, it leads to a very effective hybrid algorithm. The number of rounds of alternation is T. In each round, the classical computer has to iterate through the data set, and for each point has to do a order T calculation. The quantum computer, in each iteration, has to use Grover or whatever other optimization algorithm you like, and its inner loop also takes time order T. So if T is pretty small, this is close to optimal because you're always willing to have the classical computer iterate through the data set at least once, right? You should at least look at every data point once. You're always willing to have the quantum computer do Grover or whatever your optimization algorithm is, one time with a very small inner loop. And so if T is small, this is close to the best that you can achieve. And so yeah, so this is still a general problem, less general than the original maximum likelihood estimation. But it's one where you can really describe what the runtime is, and it's quite competitive for a hybrid classical quantum computer. Yeah, looking at the time, we should probably go to questions pretty soon, right? Or how long should I keep going on for?
Let's go on for perhaps another 5 minutes.
Okay, so this is one set of algorithms that I proposed, which is to deal with big data. And when people talk about hybrid algorithms, usually what they mean is they mean variational algorithms. And that's also kind of synonymous with NIST. And there was so what this means is you have some kind of ansatz. Let's say you start with the state size 0. You have some parameters T1 through TP that define some parameterized ansatz. This is for combinatorial optimization. This fits into the family where you're alternating applying some function as well as the sum of sigma x's. For the variational quantum eigensolver, you do something similar where maybe you split your Hamiltonian into multiple terms. And the idea is you have a classical outer loop that searches over T, and the quantum computer is used only to evaluate the objective function. So here it's a hybrid algorithm where you're using the quantum's ability to evaluate this ansatz, and the classical computer, you're taking advantage of its coherence, but not really its calculating abilities. And so one difference between this and what I proposed is to also use the classical computer's ability to access a hard drive, right? So this is it's similar in one sense of using the classical computer's coherence, but also I want to take advantage of its ability to access big data. And one thing that we worked on was replacing the function evaluations with gradient evaluations. Of course, you could even go to second derivatives, which we're looking at now. We have a way of doing efficient gradient measurements, which I think I want to skip. And we have some performance guarantees for these gradient methods, as well as a simple example where these first order strategies provably beat 0th order strategies. And what's weird about it is it's such a simple Hamiltonian. It's one that's just a sum of 1 qubit terms. But where first order methods have this provable better scaling than 0th order. However, this is all in the vicinity of a local minimum. So we've also been working on looking at what can you say about the landscape. And my former student actually, John Knapp, he just graduated, his paper is about to come out, found is that this barren plateau phenomena, where if the pulse sequence you use looks like a random circuit, then this is not a good starting point for variational algorithms. So McLean et al. Found that if your pulse sequence is long enough that it becomes a 2 design, then the gradients are exponentially small. And what John Knapp found is that yes, eventually you get to that point, but even before you reach a 2 design, your gradients are already exponentially vanishing. Basically, they go down like e to the minus order depth. And once the depth is maybe order n, then you look like a 2 design, and this is e to the minus order n. But even before then, for any value of the depth, this is already starting to decrease. My other student, Eric Anschwitz, found if you zoom in on this very flat plateau, it actually looks like an exponential number of very small little bumps. So he made some stronger assumptions. So he assumed a fairly unstructured, basically an ansatz that does not take advantage of knowledge of the structure of the Hamiltonian, and found that in that case, he can actually characterize the whole solution landscape. So here's a picture of a bumpy field. Here's actually running these algorithms on the transverse field Ising model. And you see that sort of generically, it looks super, super bumpy. You have many, many, many little bumps. And the statistics are governed by what you expect from random matrix theory. So that was the thing that Eric found. Similar things have been found for classical neural networks, and he was able to import many of their techniques to quantum variational algorithms. And that too, I hope will be on the archive in the next couple of months. So given that it's hard to find a local minimum, what should you do? So one thing that I've been working on is to find the optimal answer for an easy problem. So if you have something like the transverse field Ising model, this is an easy problem. It's equivalent to a basically non-interacting fermions. But our variational algorithms don't know this structure. And so they're sort of good they're good foils to use on this problem, or rather, sorry, this problem is a good thing to test these variational algorithms on. And what I found so far, this is still work in progress, is that this basically maps onto an instance of quantum signal processing, and that the optimization problem here is very similar to the ones that are done in qubitization or quantum signal processing or quantum singular value transform, whatever you want to call it, corresponds to optimizing. If your variational circuit is depth p, this corresponds to optimizing a degree p polynomial. And so we're able to build on the work of Guangho and others in doing this. I think I'm going to skip this slide. I'll mention one other form of hybrid algorithm that we're thinking about is how to use them for quantum simulations. Actually, here Nathan has some cool work on subsampling quantum Hamiltonians, and we've been looking at how to do this in an adaptive way. Again, using this model of an interactive classical quantum hybrid algorithm. So let me close here by saying, quantum computers are coming, we hope, but classical computers are not going away, and so we should use a model of algorithms that really tries to draw on the strengths of both. And this is a model of this idea of hybrid computing was something that Kasparov did a lot to promote after he lost to Deep Blue. Was the idea of in chess, a centaur chess is a human computer team, and for a brief glorious moment, these teams had a higher chess rating than either humans or computers alone. And unfortunately, I'm told now the computers are so good, we do not add much to their strength by playing alongside them. And this also illustrates some of the difficulties of hybrid algorithms. It's hard to have both partners in the team, being indispensable. But I do think that there's a wide range of parameters for which both classical and quantum computers can contribute useful things, and there's quite a lot to look at in this space. Okay, I'll stop here, and thank you everyone for their attention.
All right, thanks, Aram. So I'll start with a question. So these different input models, they give us a framework in which to think about the algorithms that can operate on them. Like when you have bit strings or oracles that compute bit strings, or even the more general quantum oracle, there are different frameworks that encapsulate many algorithms. Do you think, like some kind of data structure or input model that captures this kind of quantum classical hybrid computing and can allow us to think about how to use this information, similar to like how, say, quantum singular value transformations generalizes a lot of things, or how quantum box generalizes a lot of things? Could there be an idea about the framework of the right data structure for classical quantum computation?
Yeah, so that's a good point. I started off by talking about like this these categories, and then I used a model which is not quite fitting into any of those. You could say that the model that I did is a combination of the standard model where you have data on a hard drive and the oracle model, right? Because what I have is I have a data set x1 through xn, and then I also have this cost function f of xy, which I'm treating like an oracle. And so that is, how you would formalize the model that I'm describing. And then next, you could say, well, like, why should we listen to your silly model? Like anyone can come up with ridiculous models. And so then the answer is, okay, well, this model is actually one that's used a lot. So as evidence, let me just give several examples. In clustering, you have the data points you want to cluster x1 through xn, and then y is the choice of clustering, and then f of xy is how well fit is this one data point by the set of cluster centers, right? That's a plausible thing. In general, or logistical regression, similarly, x1 through xn are the data inputs you have, y are the parameters of your logistical regression, f of xy, there's some simple formula for it. And there are a few other examples in the paper, but basically, statistical questions tend to look this way, right? That you have a set of models which is parameterized by some parameters y. You can evaluate this. The log likelihood is fairly easy to evaluate for one data point in one model. That's f of xy is easy to evaluate. That's sort of a general feature in many cases. And then Right, and so that's that's why this is a plausible model. So it's not enough just to say posit the existence of an oracle, but really to make this useful, I want to be able to point to a class of problems where there are easy to compute functions f, because the cost of computing to f, that also goes in the inner loop. So if that's too expensive, that also erodes your quantum speedup.
I see.
Is that engage with what you're asking about in the question, or did I misunderstand the question?
I think you got it.
Okay.
These are early days, and then we stick with what works. Maybe one day we'll find some kind of more general framework. But the main idea is that for now we stick with things that are efficiently computable. So we might have time for one more quick question. If the audience has any. All right, so there are no other questions. So thank you very much for talking about your work today. We look very much forward to the part 2.
Great. Yeah, thanks for hosting me. Thanks everyone for coming. And Chris, I see your name on the question. I will get back to you about this. Bye everyone.